Okay, so welcome to topic 10.2. So this is going to be the first lecture for this topic. I'm going to have to do it in two parts. So this is part one. So we're going to be talking about in more detail the steps that happen inside the nephron in the formation of urine. So just to sort of review, in this slide you can see the three steps involved in the formation of urine. So the first step is filtration, and that's when blood comes into the glomerulus and some fluid passes from blood into the nephron. So that's filtration, and we talked about that already in the previous lecture. And as you may recall, the about 19% of the fluid that passes through the glomerulus gets filtered into the nephron. Okay, so and then as that filtrate passes through the nephron, it doesn't all go straight out to become urine, right? In fact, almost all of it passes from the filtrate, from the tubule of the nephron, back to the blood. That process is called reabsorption. And more than 99% of the material that gets filtered ends up getting reabsorbed and not getting excreted. Anything that doesn't get reabsorbed is going to be excreted. And actually, in addition, some material, not a lot, but some stuff is actually transported actively from the blood into the nephron, and that material gets excreted as well. So this is called secretion. So sorry, here's a table. This is all the stuff that gets reabsorbed. So almost everything gets reabsorbed, right? To some extent, anyway. And one important thing to know about reabsorption. So let's review the parts of the nephron real quick. So here, where's my cursor? So up here we've got Bowman's capsule, and then the proximal convoluted tubule, loop of Henle, distal convoluted tubule, and then the collecting duct. And the main site of reabsorption is the proximal tubule. So almost everything that gets reabsorbed here. And many things that are reabsorbed with some degree of regulation, meaning that the body can reabsorb more or less depending on the circumstances. There are two whose reabsorption is most tightly regulated, and that is sodium and water. So reabsorption of sodium and water, the reabsorption of those from the nephron back into the blood, is quite precisely regulated. Water in particular, reabsorption of water can vary over a huge range, making so that the urine osmolarity, how concentrated or dilute your urine is, can vary over a really wide range. And it turns out that, as we'll see, one of the structures that's really critical for that regulation actually is the loop of Henle. But we'll come back to that. Okay. So Sodium and water are the ones whose reabsorption is the most carefully controlled. We'll actually spend all the next lecture, what we're going to do on Wednesday, or in the next lecture, maybe not Wednesday, depending on what year we're looking at this, but then in our next lecture, we'll talk a lot about sodium and water regulation. Okay, and then secretion. This is the list of things that can be secreted. One of the things you may remember is that there are two ions, hydrogen and potassium, that can be actively secreted because your body needs to be able to get rid of these quickly because even small elevations of either of those can be very dangerous. So briefly I want to talk about just sort of the idea of what's called renal clearance. Okay, so as I mentioned, basically, so stuff gets filtered, things get pulled out in reabsorption, things get put in through secretion. Whatever makes it past those three steps is excreted, and there's a term called renal clearance, and that basically says for a given substance in the blood, how rapidly is it removed from the blood and excreted as urine? How fast is it cleared from the body? And basically, when you think about how something makes it into the urine, there are kind of two ways that you can, if you're a molecule, that you can get into the urine. One is that you got secreted. So if you get secreted into the urine, you're going to get excreted and you're going to get cleared from the body. But the other way, and actually by far the most common way for something to make it into the urine, is just simply to not be reabsorbed during reabsorption, so non-reabsorption. This is actually the main way things that are in the urine get there. They get filtered and they don't get reabsorbed. And if you're filtered and you're not reabsorbed, you will be excreted. And one of the things about non-reabsorption is that so what this graph shows is concentration of glucose in the urine on the y-axis, and then the concentration of glucose in the blood on the x-axis. And one of the basic concepts for non-reabsorption is the more of something you have in the blood, the more of it will end up in the urine. So, like for glucose, if levels are below like 250, none of it will go into the urine. But once levels start to go up above that, it starts to show up in the urine, and the more there is in the blood, the more that goes into the urine. And that kind of makes sense, right? You can just sort of imagine, and we'll talk about we'll actually look at this a little more closely, but the more that gets filtered out, the more likely it is to make it through and get excreted by not being reabsorbed. And that's basically what you're looking at here, that once levels get to be high enough, you start to excrete it, and then the more and more and more there is in the blood, the more and more that gets excreted. Okay? And you can kind of already imagine that that's actually kind of a useful thing, right? So if you have high levels of something in the blood, you will clear it faster, so you excrete it more. And if you have lower levels, you clear it more slowly. And this is actually an important way to regulate the levels of many things in our blood. We'll come back to that. Okay, so we're going to look at sort of part by part of the nephron how reabsorption works. We're going to only focus on sodium and water for now. We'll talk a little bit about other stuff later. But we're going to focus on sodium and water because those are the ones whose reabsorption is most important and most carefully controlled. And by the way, just probably obvious, but why are sodium and water so important compared to everything else? And the basic answer is that So water is by far the most common molecule in the body, right? So, if you have imbalances in how much water you have in your body, you can get in serious trouble with blood pressure, say if you're dehydrated, and osmolarity as well. If you're dehydrated, your osmolarity can be too high. And then sodium actually is the most common solute. So basically, after water, it's the most common molecule in the body. And it's the most common solute, and so imbalances in sodium can have big effects on osmolarity. And it turns out that big imbalances in sodium actually, if you eat salt, it tends to cause you to retain a lot of water also, because water will basically go with the salt because of osmolarity. So imbalances in sodium can have really big effects on osmolarity and on blood pressure and things like that as well. So both of them have really, really profound effects on physiology. So the body has to regulate them closely. Okay. So let's see. One moment. Okay. So we're going to start by looking at the proximal convoluted tubule. Okay, so this is Bowman capsule, proximal convoluted tubule. And as we said, it's the place where most reabsorption occurs. Okay, so, and here's two ways to see that. So, first of all, this list of all these things that get reabsorbed. Pretty much all of these only get reabsorbed in the proximal convoluted tubule. Okay, almost everything we're looking at on this list, they can only get reabsorbed here. So if they make it past the proximal convoluted tubule, they will be excreted. The PCT, proximal convoluted tubule, is the only place they're reabsorbed. Okay, so for a lot of substances, that's it. This is the only place they get reabsorbed. For sodium and water, about 65% of these guys get reabsorbed. By the way, we're going to be looking at, like where sodium is absorbed and water is absorbed. It's going to always say sodium chloride, which I think is kind of dumb. Anyway, ignore the chloride part. I mean, chloride goes with it too, but not significant. Sodium is the one we care about. So 65% of water, 65% of sodium get reabsorbed here in the proximal tubule. Looking at the histology, so this slide shows basically slices of tissue from each part of the nephron. So here's the proximal tubule. Here's the descending part of the loop of Henle. This is the distal convoluted tubule and collecting duct. So looking at the proximal tubule, what we see are cells that are cuboidal and that have lots of microvilli. So, and let's think about functionally what that means. So they're cuboidal, and so they have a decent amount of cytoplasm, and that's because these are cells that do quite a bit of work. So they're cuboidal rather than, say, squamous. And then they have microvilli, and you probably remember when you see cells with lots of little projections like that, these are the projections are there in order to increase surface area. And cells that have a lot of surface area, cells that do a lot of absorption, right? And so we said the PCT is where most absorption occurs. Well, these are cells that do a lot of absorption. They need a lot of surface area, thus the microvilli. So there are a couple of really important sort of, basically think about how absorption works in the PCT is quite important because it's just so much absorption happened here. Okay, so in this diagram, so here's the nephron, here's a cross section. This is the PCT. This is the capillary next to the PCT, called the peritubular capillary. And then here we're doing a zoom in on a PCT cell. Okay, so this is where the urine is. Here's interstitial fluid, right? And so the capillary would be close to here. So this is where I should say the filtrate, right? It's not really urine yet because lots of things happen to it. This is where the filtrate is, and this is where the interstitial fluid is. So the filtrate is coming by. Here are the little microvilli. And what we see are lots of transporters in the membrane of this cell. And so just some terminology to remind you about. So when we have cells, when we have an epithelium, there's a name we have for the side of the cell that faces the lumen of the tube, and that's the apical side. And then the name for the other side is basal. So it faces, in this case, interstitial, fluid, and the apical side faces filtrate. So here on the apical side of the cell, we see lots of transporters. And as you can see, all these transporters they're all co-transporters where they bring in something and sodium. So here's chloride and sodium, glucose and sodium, amino acids and sodium. So this is co-transport, or symport, as some people call it, with sodium. Now, why is it always with sodium? What does that mean? So you may remember from the digestive system, we talked about cells in the digestive tract also do a lot of co-transport with sodium. And the idea is that sodium concentration inside the cell is low. The reason it's low is that here in the basal membrane we have our old friend, the sodium-potassium pump. This is a transport protein that burns ATP to push, transport sodium out, potassium in. So it's pulling sodium out of the cell using ATP. This is active transport, pulling sodium out, keeping the sodium concentration inside the cell low. So this low sodium in here allows, it causes the sodium in the filtrate to really want to get into the cell, right? There's a big concentration gradient. So sodium in the filtrate is pretty high. Basically, it's similar to what it is in blood. Inside the cell, it's pretty low. Sodium really wants to come in. And what these transporters in the apical membrane do is they say, okay, sodium, you can come in, but you got to bring somebody else with you. Sodium, like glucose. The cell here wants glucose to come in. It wants to reabsorb glucose. But the glucose concentration inside the cell is actually pretty high because it's being pulled into the cell. And so the cell basically says, okay, sodium, you can come in, but you have to buy your way in by bringing in the glucose. And the glucose doesn't want to come in, but the sodium wants to come in so bad that the energy of sodium going down its concentration gradient is enough to pull the glucose in as well. And you may remember there's a term for this. So, this transporter here, the sodium glucose cotransporter, is it burning ATP? No. So is it an active transporter? Is that transporter an active transporter? It's not. Not burning ATP. Okay, so it's a passive transporter. But this transport, where the transporter lets sodium come in, but only if it brings the glucose with it, It's only possible because of the low sodium concentration that was created by this active transporter up here. So it's a transporter that relies on active transport somewhere else. So this is what's called secondary active transport. Okay, and all the reabsorption that happens at the PCT happens by co-transport with sodium. And so therefore it's all secondary active transport. So even though this right down here doesn't burn ATP, here at the basal membrane, the cell has to be burning ATP like crazy to keep sodium, to pull the sodium out. So you got sodium coming in like crazy at the apical membrane. So you've got to have these pumps burning, just running like mad to pull that sodium back out, keeping sodium in here low. PCT cells burn huge amounts of energy. The kidney is second only to the brain in how much energy it consumes. And that's because of these sodium potassium pumps that keep sodium inside the cell low, that allow that transport to occur. And then just to sort of finish the story of the reabsorption, so let's think about a glucose molecule gets pulled in by secondary active transport because of the desire of sodium to come in, pulls glucose in with it, and glucose in here is relatively high, so the cell just has basically channels in the basal membrane for glucose to go out the other side. Since glucose is relatively high here, it just goes passively then out into the interstitial space, interstitial fluid. So you've got passive transporters, just basically channels in the basal membrane that let the stuff pass out into the interstitial fluid, and you've accomplished reabsorption, right? The glucose is moved from the filtrate to the cell to the interstitial fluid, and then it can just pass easily into the blood, and it's been reabsorbed. Okay. So solutes basically move through and get reabsorbed by secondary active transport. Water, on the other hand, water does not have to be actively moved through the cell. Water gets reabsorbed. So water, it turns out, can pass right through these cell membranes and go from the filtrate to the cell to the interstitial fluid. So the reason, can't remember if I mentioned this before, but one thing that's kind of important to know about cells all over the body, with a few exceptions, is that cells of our bodies generally have channels in their membranes that are permeable to water. So like the PCT cells are full of these channels. These channels are called aquaporin. Aquaporin is just a channel for water. So this is a PCT cell, and it's got aquaporins all through it in the apical membrane and in the basal membrane. Water can pass in and out very readily. So water can pass right through from the filtrate to the cytoplasm to the interstitial fluid. And it does. It flows continuously from the filtrate to the cytoplasm of the interstitial fluid. But why? Why does water do that? Why doesn't water just stay here? So the answer is, let's think about when the fluid first gets filtered from the blood into the Bowman capsule. So that fluid here, this filtrate, is basically almost identical to blood as far as its solute composition. Right, it's got all the same stuff as blood except for cells and big proteins. But it's got all the, it's water and all the same ions as blood. And then, as the fluid passes through the PCT, you've got all those secondary active transporters pulling out solutes like crazy. Sodium and everything else, right, gets pulled out by secondary active transport, pulled out of the filtrate into the cytoplasm, and then that goes into the interstitial fluid. So you've got water and solutes here flowing down. The solutes get pulled out and transported across. So what's happening to the osmolarity here? as the filter is flowing. So solutes are getting pulled out. Osmolarity is dropping, meaning that basically the water concentration, the concentration of water, is going up, right? As these solutes are getting pulled out, there's more water relative, the concentration of water goes up. So there's a lot of water here. Solutes are getting pulled across here. And water, the whole concept of osmosis, water behaves just like every other molecule as far as diffusion goes. If there's a lot of water here and not as much here, more solutes in here, water's going to want to go from filtrate into cells. And guess what? It's got channels that let it do just that. So as these transporters pull solutes into the cell, water follows by osmosis. That's the way we say it. Water follows by osmosis. It follows the solutes by osmosis. You don't need to burn energy to move that water. You're burning energy to move the solutes. The water is going to want to go with it. So the water follows from the filtrate to the cell to the interstitial fluid simply by passive forces of osmosis. One of the important consequences of that, so if we think about the filtrate at the beginning, and it's basically like blood. So the filtrate's flowing down, solutes are getting pulled out, and you might think, well, so osmolarity is going to drop as solutes get pulled out. But then remember we said the water flows with the solutes, so solutes get pulled out, water goes with the solutes. Solutes get pulled out, water goes with the solutes. As the filtrate's flowing down, solutes and water are coming out at about equal proportion. So the osmolarity of the fluid, the relative concentration of solutes and water, where's my dang thing? So the relative concentration of solutes and water here is the same as it was over here, right? We're getting solutes and water being pulled out in equal amounts, and the total volume of fluid is going to be lower than it was over here. But the concentration, the osmolarity, I should say, is the same. And it's actually going to be kind of important. So if you look at, so these little numbers indicate the osmolarity of the fluid. So you get filtration into the Bowman capsule. The osmolarity of the fluid initially is about 300. Okay, that's that's the normal osmolarity of the blood, and the fluid in the Bowman capsule is osmotically, in terms of its solutes, is basically the same as blood. So 300. As fluid passes through the PCT, and by the time you get to the end, well, guess what the osmolarity is? Still 300. Is that because nothing's gotten pulled out? Is it just the fluid just passing straight through there and not changing? Well, no, not at all. Right? Tons of stuff is getting pulled out. Lots and almost all the solutes. The majority of the sodium and the majority of the water. But because solutes and water are flowing out in equal proportion, the osmolarity at this point is the same as it was at the beginning. The volume is lower, but the osmolarity is the same. And we're going to see that's keeping track of the osmolarity is going to be actually pretty important for the next part of our story. Okay, so that's the PCT. A very important part of the nephron, probably ultimately the most important part, really, because so much reabsorption happens there. All right, let's talk about the loop of Henle. So we made it through the PCT. We're in the loop. The loop has two parts. So it's got this part, which is called the thin descending limb. And it comes around, and then we're going to kind of more or less ignore this a little bit here. But then you get to what's called the thick ascending limb. So it's descending here because fluid is flowing down. And then this is ascending because fluid is flowing back up. And it literally does, so the nephron, let me kind of a more anatomical picture here. Or show you like how it looks in the kidney. No, I guess I don't have it. Dang it, good picture of that. But so hopefully you remember. So it kind of says it on the slide here. So the Bowman capsule, this sort of renal corpuscle bit up here, is in the cortex, the outer part of the kidney. In fact, most of these things are. All this stuff out here is in the cortex. The loop of Henle dips deep into the medulla and then comes back up. So when we say that this is the descending, we mean descending into the medulla, and then this is the ascending limb, ascending out of the medulla. So thin descending limb, thick ascending limb. And they're quite different. So the thin descending limb, the key thing about this part is that it's permeable to water. So water flows out as the fluid flows down, and but you know, why does the water flow out? It's not super obvious that would happen. The reason is, and this is going to be quite important, so we'll explain why it happens later. But just for now, just be aware that the interstitial fluid of the kidney, so the fluid around the tubule, its osmolarity changes as you go from cortex to medulla. So out here in the cortex, the fluid around the kidney has an osmolarity of about 300. So the same as the fluid inside the nephron here. Same as blood, really. But as you go deeper into the medulla, the osmolarity of the fluid here around the nephron gets higher and higher and higher, more and more concentrated. So it gradually increases to 1200 milliosmolar at the deepest part of the medulla. And so osmolarity is quite high out here, so you've got this fluid with an osmolarity of 300, so not super concentrated, fair amount of water flowing down here. The tissue around becoming more and more concentrated. So if you've got high concentration of solutes out here, as the fluid flows down, water is going to want to go from filtrate into interstitial fluid, right? High concentration out here, so the water flows out of this thin descending loop of Henle, because the concentration of the interstitial fluid is so high, water wants to flow out into it. And so one of the consequences of that, let's follow these numbers. So again, at the end of by the end of the PCT, the osmolarity is 300. Well, you start to dip into the thin descending loop of Henle. You start to go down into the medulla, and you'll see the osmolarity start going up and up and up. It basically matches the osmolarity of the interstitial space, because water can pass out. Okay, so that's what happens in the thin descending limb. And then the thick ascending limb, you have a couple important things. So first of all, it's not permeable to water. Water cannot pass out of the thick ascending limb. And then the other thing that's important about the thick ascending limb is that it actively pumps out sodium all the way up. Sodium's getting pumped out. Water is not allowed to go with it. Okay, and so we're going to see what this is all about and why that matters in a little bit. So that's actually quite unique, really anywhere in the body, to have no water permeability. Almost every cell in the body is permeable to water. These cells of the thick ascending loop of Henle are quite unique in that they are not permeable to water. Let's talk a little bit about the thin and thick ascending loop as far as histology goes. So here's the thin descending loop, and the histology of this part of the loop is simple squamous, so thin cells and single layer, so very thin walls. highly permeable. It makes it very easy for the water to flow out. One thing I didn't mention, but these cells do not do any active transport. Sorry, one moment. Okay, sorry about that. So these cells in the thin descending limb do not perform active transport, and so they don't need much cytoplasm, right? And so they're squamous. They just make it as easy as possible for water to flow out, and they don't do any active transport. Whereas the cells of the thick ascending limb of the loop, this is not very anatomical, but basically shows that they look more like the PCT cells, in that they're cuboidal, and they have microvilli. And they're cuboidal because they do a lot of work, right? They need ATP. You need cytoplasm. They do a lot of active transport of sodium, other stuff as well, but sodium is going to be the main one we care about. So you can see here that cells are transporting sodium in and then transporting it across the basal membrane, right? The other side. So actively pumping sodium across from filtrate into interstitial fluid. And then the other thing, as we mentioned, the other unique thing about these cells is that they're not permeable to water. They do not have any aquaporins. Okay. Okay, so that's loop of Henle. We're going to come back to that, actually cover that for the rest of the majority of our lecture after we finish our summary here. So we're out of the loop of Henle. We're here and then we have the distal convoluted tubule and the collecting duct. And this is where basically the remainder of sodium and water reabsorption occurs. So anything, basically obviously that makes it past the collecting duct, that's going to become urine. So this is the last chance to do sodium and water reabsorption. The main thing to know about reabsorption that happens here in this section is that it's regulated by hormones. And we're going to spend the whole next lecture talking about how that works. But so you may have noticed that reabsorption in the PCT and in the loop, it just happens, and it kind of happens all the time at the same, basically the body doesn't change how those cells are behaving. It doesn't change what those cells are doing. They kind of do what they do all the time. They're not regulated actively. The DCT and collecting duct, on the other hand, can change how much or little that they reabsorb. And that the way they change, the way the body changes that is by the action of hormones. So the two hormones are hormones that control sodium and H2O, sorry, my handwriting, reabsorption at the DCT and collecting duct. That's terrible. Okay. First one is aldosterone. And that hormone controls sodium reabsorption, mostly at the DCT. A little bit in the collecting duct as well, but mostly the distal collecting tubule. Okay, so aldosterone, you may remember, is synthesized by the adrenal cortex. It's actually under control of this complex system, renin, angiotensin, aldosterone system, and we'll go through how that works in the next lecture. So aldosterone released from the adrenal cortex, it comes down to cells of the DCT mostly. It's lipid soluble, so it passes through and binds to intracellular receptors. And when it does that, it then the final result is that the cells of the DCT basically put more sodium transporters in their membrane. So aldosterone, so increase in aldosterone leads to increased sodium reabsorption at the DCT. So you can see that, so you know, the body actually can change the cells. When there's more aldosterone, it puts more transporters in the cells, more sodium gets reabsorbed. Okay, and then the other hormone is called ADH, or antidiuretic hormone. And that hormone controls water reabsorption at the collecting duct mostly. So that works. ADH comes along, binds to receptors, so it's water-soluble hormone, binds to receptors. Don't forget there's a cumulative final coming up. So it binds the receptors on the cell surface, triggers blah, 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 intracellular messenger stuff. And it causes cells of the collecting duct to place more aquaporins in the membrane. More aquaporins mean more water goes from filtrate through the cell into the interstitial fluid and into the blood. So more ADH leads to more aquaporins, which leads to more water reabsorption at the collecting duct. And by the way, I should probably give a little more information up here too. So more aldosterone leads to more sodium. Dang it, gotta move this over more. There we go. More sodium transporters in DCT cells, and that leads to more sodium reabsorption. And similarly, more ADH leads to more aquaporins in the collecting duct, and therefore more water reabsorption at the collecting duct. And then, last slide for this part of the lecture, just a summary of the different parts of the nephron, and you know, and basically their water, sodium, and other solutes reabsorption. So here in the proximal convoluted tubule, you have high reabsorption of everything, including water, sodium, and other solutes. So this is the only place where basically other solutes, any other solutes are reabsorbed. They're not reabsorbed anywhere else except the PCT. But sodium and water are also highly reabsorbed here. Okay. Then in the thin descending loop of Henle, you get lots of water passing out, but no sodium reabsorption, basically. These cells do not pump sodium out. And then the thick ascending leukopenly, you get the opposite. So they're not permeable to water, so you get no water reabsorption, but you get lots of sodium being pumped out. And then finally, the DCT and collecting duct, they can reabsorb water and or sodium, but that reabsorption is variable and it's under the control of hormones. Okay, so that'll do it for this part, and then we'll do part 2.